Hello. So in this video and also in the next video, we will discuss about brute force, which is a very simple technique to construct an algorithm. And the algorithm itself is called a brute force algorithm. So these two videos will learn about definition, advantages, and disadvantages of brute force. Also, brute force algorithms, some example of brute force algorithms that are based on related concepts or problem statement, and also brute force algorithms for combinatorial problems, and also some exercises. But for this video, we will focus on these two, and the other two are from for the next video. So we start with definition, advantages, and disadvantages. So brute force algorithm is a straightforward approach to solve a problem. It is usually constructed based on problem statement and also definition of related concept. Brute force algorithms solve problems in a simple way, straightforward, and in an obvious way. Generally, a brute force algorithm is not smart and not efficient because we really just need to know what the problem is. We need to understand what the problem is and how we do solve the problem without computer. So we then just need to construct an algorithm based on that. And that's why it's not efficient because we don't really need to think much about how we can have a solution as fast as possible. And the word force in brute force indicates power we use to solve the problem instead of brain we use to build the algorithm. And it is also known as a naive algorithm because of its straightforwardness and because we really just need to know what does the problem mean. That's why it is a naive algorithm. And it is a simple and easy to implement, so that is it is useful for problems with small size, but for problems with large size, because of its efficiency, it is not really good to be used. Often used for comparison with more efficient algorithm, because we know that this algorithm is not efficient, so we want to know if we have an efficient algorithm when we compare it with brute force algorithm. And almost all problems can be solved by brute force, and even some problems can only be solved by brute force. For example, determine the largest element in a list. So the advantages of brute force that it can be used to solve almost all problems. So it has a wide applicability, and it is simple and also easy to comprehend, and it can produce acceptable algorithm for some problems. For example, searching, string matching, and matrix multiplication, because we really need to find all elements we have to search or match or to do matrix multiplication. And also, we can produce a standard algorithm for computational problems. For example, for addition or multiplication, and also determine minimum or maximum value in a list, we can use brute force. However, the brute force technique rarely produce an efficient algorithm, and some brute force algorithms are really slow, such that they are not acceptable. Like maybe you will find a runtime error when you implement the algorithm. And it is not a creative way to solve a problem because it really just based on the problem statement. We don't need to think how can we have a faster algorithm to solve the problem. So we will give you some brute force algorithms example that are constructed based on related concepts or the problem statement itself. For example, if we want to have a power of integers, so if we want to have to compute a to n, where a is larger than 0 and n is a non-negative integer. Mathematically, we can solve it like this. So if n equals to 0, a to n is 1, but otherwise we just need to multiply n many a's. So the algorithm will be multiplying 1 with n many a's. The next example is to compute factorials. If we want to compute n factorial, where n is a non-negative integer, in mathematics we can use this relation, that is, if n equals to 0, then n factorial is 1. Otherwise, if n is larger than 0, we have n factorial is 1 multiply with 2 and so on until n. So the algorithm will be we return 1 if n equals to 0, or otherwise we just need to multiply n first positive integers that are 1 to n. And the next problem is multiplication of two matrices of size n times n. So in mathematics, we can have for example, we have matrix A. We can write it like this: AA1 until A1n, and we have this until AN1, and so on until ANN. And if we have B, then we have B11 until B1n, and BN1 until BNN, so that if we have C is the multiplication of 2, we can have the first element of C here is the multiplication of this vector times this vector. So basically every element we have here in C is the multiplication of two vectors with size n. So the algorithm will be to compute each element of C one by multiplying two vectors of size n. This is a pseudocode for that. So here we need to do the multiplication for each row we have with considering each column we have, and then we find the value of Cij by adding the multiplication we have for the vectors. And if we consider complexity of the algorithm, here we can see that we have three loops here, when where each loop has to be completed n times. So we can see that it has big O n to 3. Another example is to find a factor of an integer. So we want to find all factors of a positive integer n beside 1 and itself. A factor itself is defined like this. An integer a is a factor of an integer b if a divides b. A divides b here means that we have c such that this holds, or we can say that b is equivalent to 0 in modulo a. Or we can also say that if we have b modulo a, it's equal to 0, something like that. So how can we find a factor of an integer b, or of an integer n? The input is n. Of course, we just need to check one by one from 2 to n minus 1 if there is an integer that divides n. If so, then we write the value. This is the illustration for the algorithm, and this is the pseudocode for the algorithm. So the first one, we have k equals to 1. if k, and then we check from k 2 until n minus 1. If n mod k is 0, it means that k is the factor of n, so we just need to write k, and so on. And we can see these only have one loop that is iterate n minus 2 times, so that the complexity of the above algorithm is in big O n. And if we want to find largest element in a list, so given a set of cardinality n whose elements are integers, and the elements are represented by a1 to an, we want to find the largest element in the set. So like the problem set statement itself, we just need to check from a1 to an one by one and always store the largest element so far. First, because we don't have anything to compare, we uh, assume first that a1 is the maximum, the largest one. And then we compare max with a2. If max is larger, we move to the next target, but if it's not, then we update the max, and so on until we have a. We check an so that we can have the largest element stored in max. This is the pseudocode for the algorithm. So first we assume that a1 is the max, and then we check from a2 to an. If there's any that larger than max, then we always update the max. Here we only have one loop, which is iterate n minus 1 time, so the complexity is big O(n). Another example is sequential search. So the problem is given n integers that are represented as a1 to an, we want to determine whether an integer x is in the set. If x is found, store the index of the element to variable idx. If x is not in the set, idx is 0. So the algorithm will be checking the integers from a1 to an one by one. If there is an element equal to x, we store the index, otherwise store 0. Basically, it is the same, similar like before, but we check from k1 up to n minus 1. Sorry, yeah. And then we stop the loop if we already found x, or otherwise we move to the next element, and we stop the loop if we reach k equals to n or x is found. And if k equals to n, we check if ak is x or not. If yes, then the idx is k, or otherwise it means that we don't have x in the list, so x is not found. Here we only have one loop, which can iterate up to n minus 1 times, so the complexity of the algorithm is in big O(n). The next example is bubble sort. So given a table consists of n integers, we want to sort the table in ascending order by using bubble sort method. So let us recall bubble sort. This is a sorting method that uses element swap in the process, and the main idea is to bubble up the lowest element by swapping adjacent element. So if we have a1, a2, and so on until an1, n minus 1 and an. We in bubble sort we will have some paces from pace 1 to pace n minus 1, where in pace 1 we first check an and an minus 1 and check if an is larger than an minus 1. If not, if an is smaller, then we swap them. So we always want the smaller number is on the left position. So uh, after we swap, we then compare it again with the next adjacent element. And like before, we want to always have the left one to be the lower. So we swap if we need to swap, or go to the next element if we don't need to swap, and so on until in the pace one, a1 is the lowest element. For pace 2, we repeat the same thing, but we just need to do it from an to a2, so that we have a2 is the second lowest element, and so on until we have an1 is the second largest element, and automatically an is also the largest element. So here, as an illustration, the algorithm we'll have for the first pass, we check the elements one by one from the last element by comparing with its adjacent elements. And every time the earlier element is smaller, we swap the elements so that the smallest element will be placed in the first position. Repeat for the second pass so that the second smallest element is placed in the second position, and so on until we have the largest element in the last position. So this is the pseudocode for that. We have pass 1 to n minus 1, and then we compare the elements from an to I plus 1, and then we swap if necessary, and we do it until we have the final pass. So here we have two for nested, and the first one can iterate up to n minus 1 times, and the second one can be iterate up to n minus 1 times as well. So the time complexity is obviously in big O n to 2. The next example is primality test. Given a non-negative integer n, and we want to test if the integer is a prime or not. So, sorry, this is a not non-negative but positive. So from the definition itself, prime number is an integer larger than 1 that can only be divided by 1 and itself. So the algorithm will be, if n equals to 1, then n is not a prime number. If n equals to 2, then n is a prime number. And if n is larger than 2, if larger than 2, check if there exists an integer from 2 to square root n that divides n. If there exists such integer, then n is not a prime number. Otherwise, it is a prime number. So basically, we do similar thing with what we have done in finding factors of an integer. However, here we only need to find to check a square root of n elements, because like if we have 12, for example, as n, then the factor will be 2, 3, 4, and 6. Well, if we don't consider 1 n itself as the factor. And so we can have divided like this. If we have 3, we must have 4, and we have 2, then we have the 6. Also, like if we have 9, then the factor is 3, and 3 is pairs with itself basically. So yeah, we just need to check from 2 until square root n, but we uh, take the larger integer of that. So yeah, the algorithm will be, if x less than 2, then we return false because it is not an integer. If x equals to 2, then we return true because it is an integer. This is a special case because square root of 2 is 2. So it's not really what we want to have, like something in between. So this is a special case. But other than that, we have this loop where y starts from the square root of x, and we do it until we reach y equals to 2. We always do it backwards, and we check if y divides n or not. If it is, then test is false, so we get out of the loop. And otherwise, we still loop until we have y equals to 2, which means that there is no factor other than 1 and itself. So n is a prime. And if we consider complexity, here we have one loop here, which iterates square root n times in the maximum, in the worst case. So the complexity is in big O n. And the last example is computing polynomials. So if we want to compute the value of polynomial, we have here px at x equals to x0, then obviously we just need to add the result of the multiplication we have. And the multiplication itself, we just need to uh, multiply an with x n times, right? So we'll have this pseudocode as the algorithm. So here we have p as the result, and then the result is 0 at first because we don't have any addition yet. And then we do the multiplication from the highest degree first. So from x to n, we first compute x to n by doing this algorithm. So yeah, we multiply 1 with x0 n times, and then we multiply it with an, and we add it to the result, and so on until we do it to a0. And yeah, we finally have the p, and here we have 1 2. So we have nested loop with 2 layers where 1 is done n plus 1 times, and here we do it up to n times. So the times complexity is obviously in big O n to 2 or n squared. Yeah, that's all for this video. We will continue the brute force topic on the next video. It will be about exhaustive search. See you later.